Hey everybody, today I'm going to be talking about the hyperreal numbers. For this presentation, I'm assuming some background. First of all, I'm assuming that you have seen calculus, at least basic differential calculus that touches on the concepts of limit and continuity and derivative. If you haven't seen those, this talk probably won't be very meaningful to you. Secondly, ideally, you may have seen some abstract algebra touching on the concepts of ring and field and quotient. If you haven't seen those, I will be covering them informally, but you'll get more out of the presentation if you've seen those before. And finally, I'm assuming a little bit of familiarity with logic, in particular with the concept of a first-order language. So first, let's cover a little bit of history. As a warning, I am not a historian, so this is a little bit oversimplified. In the history of calculus, mathematicians like Leibniz and Newton freely used infinitesimals in calculations. Now, an infinitesimal is intuitively just an infinitely small number. Let's take a look at an example of how infinitesimals would be used to show that the derivative of x squared is 2x. So here is a quote-unquote proof using infinitesimals. If dx is an infinitesimal change in x, then the corresponding change in y is just dy, the quantity x plus dx squared minus x squared. So if we compute the quotient dy over dx, algebra just gives us that this is equal to 2x plus dx. But since dx is infinitesimal, we can just ignore it, and dy over dx is 2x, which is the derivative that we wanted to compute. Of course, this argument is nonsense. If dx is 0, then we can't divide by it in computing dy over dx. And if dx is non-zero, then we can't ignore it, at least assuming that dx is an ordinary real number. Here, it's useful to pause to recall why we can't divide by 0 in the first place. The answer is this. For numbers a and b, the quotient a over b should be a unique number c, such that a is equal to b times c. Now, if b is equal to 0, then b times c is just 0 for all c. That's because 0 times anything is always 0. If a is non-zero and b is 0, then there is no c satisfying a is equal to b times c. On the other hand, if a is 0 and b is 0, then any c satisfies a is equal to b times c. So in either case, it doesn't make sense to define a over 0. Some mathematicians and philosophers criticized the use of infinitesimals in calculus along these lines. George Berkeley famously called infinitesimals ghosts of departed quantities. Eventually, the criticism won out. The use of limits, with formal definitions in terms of epsilons and deltas, came to replace the informal use of infinitesimals in mathematical proofs. These are just the limits you know and love from calculus. The theory of limits was developed by mathematicians like Cauchy and Weierstrass in the 1800s. However, infinitesimals were intuitive and they worked. Leibniz had thought of them as useful fictions, just as he had thought of imaginary numbers like I, the square root of -1. His notation for infinitesimals is still used in modern calculus for both the derivative and the integral. In this context, d over dx and integral dx are understood as operators with no independent meaning assigned to the symbol dx. In 1960, Abraham Robinson developed a system of hyperreal numbers, extending the system of real numbers by adjoining infinitely small and infinitely large numbers. With hyperreals, it's possible to legitimately use infinitesimals for calculus. This is part of Robinson's theory of nonstandard analysis, which not only simplifies classical definitions and theorems and proofs, but has also led to a number of new discoveries. Now, Robinson originally developed the hyperreals using tools from mathematical logic, like the compactness theorem. In what follows, I'm going to present a more direct algebraic construction. This construction is similar to the construction of the real numbers using equivalence classes of Cauchy sequences of rationals. But first, we need to cover some preliminaries. First, recall that a ring is a set with addition and multiplication operations defined on it, satisfying familiar properties like commutativity and associativity and distributivity and so on. Note, we're going to assume that a ring is commutative under multiplication and has a multiplicative identity. A field is just a ring in which we can also divide by non-zero elements. So for example, z, the set of integers, forms a ring under ordinary addition and multiplication. But it's not a field, because 2, for example, doesn't have a multiplicative inverse in the integers. In other words, 1/2 is not an integer. On the other hand, the set Q of rational numbers and the set R of real numbers form fields under ordinary addition and multiplication, because there we can divide by non-zero elements. In what follows, I'm going to construct an ordered field *R, the hyperreals, extending the reals with infinitely small and infinitely large elements. First, we need to review a little bit of algebra. Recall that for a ring R and a special type of subset I of R called an ideal, we can form what's called a quotient ring, R mod I, by intuitively identifying all of the elements of I with 0, and then using the same algebraic operations. In order for this to work, I needs to be closed under addition and under multiplication by any element of the ring. If you haven't seen this before, this sounds a little bit wacky, but hopefully this example will help clarify. If 12z denotes the set of integral multiples of 12, then the quotient ring z mod 12z is just the ring of ordinary 12-hour clock arithmetic. In this ring, 13 is equal to 1, since 13 is just 12 plus 1, which is 0 plus 1, which is 1. And 27 is equal to 3, since 27 is just 2 times 12 plus 3, which is 0 plus 3, which is 3. Now, technically speaking, in the quotient ring, the objects are not integers, but for our purposes, it's easier to think of them as integers, some of which have been identified. The whole idea here is that we've been able to identify all of the multiples of 12 with 0 and still preserve the algebraic operations of addition and multiplication in a way that satisfies all the properties of a ring. Now, if an ideal M is large enough to be what's called maximal in a ring R, then the quotient R mod M is actually a field, and the converse is true too. This means that M is not equal to R, but it's not contained in any ideals other than itself and R. As an example, the set 3z of integral multiples of 3 is maximal in the integers, so the quotient z mod 3z is actually a field. In this field, the number 1/2, that is the multiplicative inverse of 2, is just 2, since 2 times 2 is 4, which is 1. Importantly, for any ideal I that's not equal to R, there is a maximal ideal M containing it. This follows from the axiom of choice in set theory. So this means if we want to identify all the elements of I with 0 to produce a field, we actually need to identify the elements of M with 0, forming the quotient R mod M. That covers the basic algebra that we'll need, but before continuing, I need to say a few words about large sets. So consider an infinite set X and a collection U of intuitively very large subsets of X, each of which contains almost all of X. What are some nice properties that we might hope U satisfies? Well, first of all, if S is in U and S is a subset of T, then it would make sense that T is in U. In other words, supersets of large sets should also be large. Similarly, if S and T are both in U, then it would make sense that their intersection, S intersect T, is also in U. That is, intersections of large sets should be large. Another way to see this is that if S and T are both large, then their complements are small. And the complement of their intersection is just the union of their complements, which is therefore a union of small sets. It makes sense that the union of two small sets is small. Next, if S is an arbitrary subset of X, then it would be really nice if either S is in U or its complement is in U. In other words, either S is large or it's small. Although you can potentially envision cases where that wouldn't be true, this is a very nice property to have because it simplifies the possibilities for subsets. Finally, if S is an arbitrary finite subset of X, then it shouldn't be in U. Since X is infinite, any finite set is small and therefore not large. If U satisfies these properties, it's called a free ultrafilter on X. Now, I'm not going to explain that naming, you can look it up if you're interested, But for our purposes, a free ultrafilter on X is intuitively just a well-behaved collection of very large subsets of X, which means by definition it satisfies the properties listed here. Now you might wonder whether I can give you a concrete example of a free ultrafilter. And unfortunately, the answer is no. Although it's possible to establish the existence of free ultrafilters using the axiom of choice, as we'll see in a moment, it's actually impossible to construct an explicit example of one. With these preliminaries out of the way, we can now construct the hyperreals (R). So we start with the intuition that an infinitesimal, unlike an ordinary real number, should be a variable quantity which vanishes. This intuition is actually present in some of the writings of Leibniz and Newton and other mathematicians like L'Hopital and Cauchy. If we take this idea seriously, it leads us to model infinitesimals not as real numbers, but as real-valued functions of time, which vanish over time. For convenience, we're going to use the natural numbers n as a discrete time axis, so infinitesimals are just sequences of real numbers which converge to zero. By contrast, an ordinary real number r corresponds to the constant sequence, all of whose entries equal r. Now we can add and multiply these sequences component-wise, as seen here. This forms a ring R with additive identity 0, the constant sequence 0, and multiplicative identity 1, the constant sequence 1. However, this ring R is inadequate for our purposes for a couple of reasons. First of all, it has many eventually zero sequences, that is, sequences that become and stay zero after finitely many terms, like 3, 2, 1, 0, 0, 0, and so on, which we intuitively want to treat as zero. If a sequence becomes and stays zero after finitely many terms, it's only trivially different from zero, and so we want to just identify it with the zero sequence. Secondly, this ring has many non-zero sequences without multiplicative inverses, like the sequence I just listed, so it's not a field. However, we can solve both of these problems using techniques we've already described. The set of eventually zero sequences forms an ideal in R, so if we let M be any maximal ideal containing it, then the quotient R mod M is actually a field, in which the eventually zero sequences have been identified with zero. This leads us to our definition of the hyperreal numbers. The hyperreals are just given by R mod M, which is denoted (R). Note that R is a subset of (R) under the identification of a real number with its constant sequence. Now, as a warning, I'm not going to be distinguishing notationally or even verbally between sequences in the ring R and their residues in (R), although technically these are different objects. This is just like the situation with clock arithmetic earlier, where I didn't distinguish between integers before and after the identification of all the multiples of 12 with 0. Here, I'm not distinguishing between the sequences in R before and after the identification of all of the sequences of M with 0. We're just going to pretend that these elements of (R) are sequences, some of which have been identified. So the question naturally arises, what do the sequences in M, which we have identified with 0, actually look like? This leads us to a few definitions. First, for a sequence A in the ring R, let Z of A be the set of indices where the sequence is 0. I'm going to call this the zero set of A. Next, let UM be the collection of all zero sets of the sequences in M. Then it turns out that UM is actually a free ultrafilter. In other words, it's intuitively a well-behaved collection of very large subsets of the natural numbers. So a sequence is identified with 0 in R if and only if almost all of its entries are 0, and two sequences are identified with each other if and only if almost all of their entries are equal. Now note that although UM provides an example of a free ultrafilter, it doesn't count as an explicit construction because we use the axiom of choice to get M. Now that we have a better understanding of what the elements of (R) look like, we examine operations on (R). So, given a function f on R, how can we naturally extend it to a function (f) on (R)? The answer is this. For a sequence A in (R), we just apply f to the values of the sequence. So (f) at A is just the sequence whose values are f of an. Note that star f is well defined since is an ultrafilter. In other words, if A is equal to B in star R, then that means that AN is equal to BN for almost all n, so f of AN is equal to f of BN for almost all n, and therefore star f at A is equal to star f at B. Now, this same basic idea works for functions of multiple variables from Rn to R. And using characteristic functions, we can also extend subsets and relations from R to star R. For example, if we define fn, the characteristic function of the naturals in the reals, which assigns the value 1 to natural numbers and 0 to real numbers that are not natural, then we have an extension star fn, and we can use that to define the extension star n of the natural numbers in star R. Notice star n contains n and consists of sequences in star R, almost all of whose entries are in n. Similarly, if less than or equal to denotes the ordering on R, we can define its characteristic function f less than or equal to on R2 by mapping the pair xy to 1 if x is less than or equal to y, and to 0 otherwise. We can then define A to be less than or equal to B in star R if star f less than or equal to of AB is 1 in star R. It follows that A is less than or equal to B in star R if and only if AN is less than or equal to BN for almost all n. Now, one of the most important things about the hyperreals is that we can transfer certain properties from f to star f and vice versa using a transfer principle. This is the transfer principle. If phi with free variables x1 to xn is a first-order formula in the language of the ordered field R, and R1 to Rn are fixed real numbers, then R satisfies phi with R1 to Rn substituted for x1 to xn, if and only if star R satisfies it also. This means that any first-order statement that's true of the real numbers is also true in star R and vice versa. This is an extremely powerful tool when working with the hyperreals. Now, the proof is by induction on the formula phi using the ultrafilter properties of but I'm not going to provide the proof here. Instead, let's take a look at a simple example of how the transfer principle can be used. In the real numbers, we know that addition is compatible with ordering in the sense that R is less than or equal to S if and only if R plus T is less than or equal to S plus T, and this holds for all real numbers R, S, and T. But this means that R satisfies the first-order sentence seen here. By the transfer principle, that means that star R also satisfies that first-order sentence. And that means that addition is compatible with ordering in star R. Notice this tells us that addition of hyperreal numbers is compatible with the ordering that we've defined on the hyperreal numbers. So we've been able to transfer something that's true in the reals to something that's true in the hyperreals using this transfer principle. Similar arguments show that star R is an ordered field. Importantly, higher order properties of R like completeness, which quantifies over subsets of R, do not transfer to star R by the transfer principle. After all, star R is very different from R, so we shouldn't expect everything to transfer over. Now let's revisit infinitesimals in the context of the hyperreals. First, let omega be the sequence 1, 2, 3, and so on in the extended natural numbers. For any real number R in star R, it's clear that R is less than omega, since R is less than n for all but finitely many n. So omega is infinitely large. It follows from the ordered field properties that 0 is less than 1 over omega, which is less than 1 over n for all natural numbers n. So 1 over omega is infinitely small. Note that 1 over omega is just the sequence 1, 1/2, 1/3, and so on in star R. This means that star R is an ordered field extending R with infinitely small and infinitely large elements, which is what we wanted. Now we can introduce some additional definitions. A number A in star R is called infinitesimal if its absolute value is less than 1 over n for all positive natural numbers. If A and B are in star R, then A is said to be infinitesimally close to B, written in this way, if A minus B is infinitesimal. So A is infinitesimal if and only if it's infinitesimally close to 0. These definitions allow us to use infinitesimals for calculus. First, we characterize functional limits. If f is a function on R and a and b are two real numbers, then the limit as x approaches a of f of x is equal to b if and only if star f of x is infinitesimally close to b whenever x is infinitesimally close to a but not equal to a. Notice this result is extremely intuitive, and this could serve as the basis for a more intuitive definition of functional limit than the ordinary one given in calculus. The proof of this result uses the transfer principle. Unfortunately, I don't have time to cover it in this presentation, but I highly recommend you look it up because it serves as a beautiful illustration of the use of the transfer principle. We can use this result on functional limits to characterize continuity. A function f on R is continuous at a real number a if and only if star f of x is infinitesimally close to f of a whenever x is infinitesimally close to a. This follows immediately from the limit theorem and again is extremely intuitive. The intuitive notion of continuity is that an infinitesimal change in x results in an infinitesimal change in f of x, and that's exactly what this says. The limit result also allows us to characterize differentiability. First, we introduce a definition. If f is a function on R and x is a real number, then we let df be star f of x plus dx minus f of x for dx infinitesimal. Notice that df depends upon both x and dx and represents the change in f at x given an infinitesimal change in x. Now we obtain the result that a function f on R is differentiable at a point x in R with derivative f prime of x if and only if df over dx is infinitesimally close to the value f prime of x whenever dx is infinitesimal and non-zero. Notice here that df over dx is an actual quotient of two quantities df and dx in star R. In this case, dx is not just a meaningless symbol. In other words, Leibniz has been vindicated. This is just a small taste of what it's possible to do with hyperreals in calculus. These same techniques can be used to develop all the classical results of calculus and to go far beyond. I highly recommend that you read more about it. Here are the specific resources I used in preparing this presentation. Thanks for watching.